Last week, we talked about how to find our exponents by adding the exponents if the bases are the same, or subtracting them if the bases are the same and the exponents are different. So let's take a look at this example again. My base right here is the same. My base is 5 and my base is 5. The only thing that changes is my exponents. We lay them out by saying we have 8 5s. So 5 times 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 5. And then we have another 5 set of 5. So 1, 2, 3, 4, 5 5s. Okay, and all we're doing is we're just simplifying the problem. Instead of writing all of these 5s out, we're just adding 8 plus 5. And this is only if the base is the same. Okay, this n, this variable, or n is the same. This is our formula for multiplying exponents. Okay, down here we have our formula for dividing exponents. It is similar to our multiplying, except with our exponents, we're subtracting the exponents if the base is the same. Okay, so let's reflect. Okay, I'll give you a couple seconds here to fill this form out down at the bottom on page 5. All right, your explanation should look something similar to this. Because I have 10 5s in a product and I divide it by 2 5s in a product, it's the same as 8 5s in a product, or 5 to the 8th power. Alright, so let's review this part right here. We talked about different powers and multiplying different powers together if the base is the same. What did we say that happened here if we multiplied 3 to the 2nd power to the 4th power? That's right, we multiplied it together. 2 times 4 equals 8. Now that we got through our review, let's take a look at zero and negative exponents. We touched upon this last week, so we're going to wrap up with this week. Okay, it says read the problem below and then explore simplifying expressions with exponents equal 0. Okay, anytime you see an exponent of 0, that means that your product is always going to be 1. Okay, so let's take a look at why that is. Okay, it doesn't make sense if you ask yourself, what is 0 5s multiplied together? It doesn't make sense at all because there's 0 5s. Okay, we need to approach this problem in another way. So far, we've worked with powers where exponents are counting numbers 1, 2, and 3, and so forth. And then the rules for working the powers are the same when the exponent is 0. You have seen when you multiply the powers with bases that are the same, you add the exponents. So if there's 5 to the 0 power times 5 to the 4th power, now look, my base is the same, my base is 5, okay? All I have to do is multiply 5 times 5 times 5 times 5 times 5, 4 times, because there's 0 5s over here, okay? That would make my answer 5 to the 4th power. So let's take a look at how we did it down here if we multiplied everything by 1. Okay, let's apply the identity property of multiplication, where if we multiply anything by 1, it holds its own identity. So let's multiply 5 to the 4th power times 1. What do we get? 5 to the 4th power, because 1 times 5 to the 4th power is 5 to the 4th power. So therefore, 5 to the 0 power times 5 to the 4th power is 5 to the 4th power. So your 5 to the 0 is always going to be 1. Your 1 to the 0 is going to be 1. Your 2 to the 0 is going to be 1. Your 3 to the 0 is going to be 1. So on and so forth. Anything to the 0 power is always going to be 1. And then you can simplify that by multiplying that to whatever problem you have. So 5 to the 0 power is going to be 1. I'm going to make that font a little bit bigger. You can see it. It's too big. Okay, so let's take a look at 12 to the 0 power. Go ahead and fill these 3 out for number 14. Alright, so if we complete these examples, 12 to the 0 power should be 1. Any number really, if you put here and you put this as to the 0 power, is going to equal 1, and negative 7 to the 0 power will also equal 1. Okay, it's not a negative 1 or a positive 1, it's just a 1. Okay, any possible number should go here. So, in general, for a power where the exponent is 0, if that exponent equals 0, then n to the 0 power is going to be 1. Okay, so the rules for the products also apply when the exponent is a negative integer. So you have down here 5, 6 to the 5th power, times 6 to the negative 5th power, it's going to equal 6 to the 0 power. Okay, and that is going to equal 1 because you're doing opposites with each other. You're canceling them out. You already know that a number times its reciprocal equals 1. So let's take a look at our fractions. Remember when we had 3? We had 3 over 1. Okay, there would be a 1 here. Times 1/3, that would equal 3 over 3. And 3 over 3 as our fraction is 3 parts over 3 wholes. That would equal 1. So let's complete equation 6 to the 5th power times 6 times 1/5 times, 1 over 6 to the 5th power. Okay? That would make this 6 to the 5th power over 6 to the 5th power equals 1. Let's take a look at number 18. Since 6 to the 5th power times 6 to the negative 5th power is 1, just like we said up here, that means 6 to the 5th power times 1 over 6 to the 5th power equals 1, because you're putting this 6 to the 5th power actually over here. Okay, so then that means that 6 to the negative 5th power would equal 1 over 6 to the 5th power. Alright, so let's try some of these examples right here. What would the answer for 1 to the negative 6th power mean? It means we're going to change it to its reciprocal. We're going to change it into a fraction. So it's going to be 1 over 10 to the 6th power. So we have 1 to the 6th power. Okay, the goal in this right here is to try to make it positive in this equation. So that's why we make it a reciprocal. We make it 1 over 10 to the 6th power. Here, I want to get rid of my negative exponent once again. So what do? I make it the reciprocal. Note that the negative 34, our base number, stays the same. Notice how I just bring it over here, but I bring it into my denominator. It's still negative 34 because it's in parentheses. I keep it like that. I make my exponent the 7 instead of negative 7. And same goes for here. If I was given a fraction here, I would make it into a negative if I wanted to make it a whole number. So I would have, instead of 1 over 142 to the 13th power, it would become 142 to the negative 13th power. All these numbers equal its reciprocal. So here, in general, for a power where the exponent is a negative integer, where n to the negative a, where n is to the negative a, I'm going to say it's going to be 1 over n. This is your formula. To the a power. Now you try it. Let's use what we just learned to solve these two problems here. Go ahead and hit pause and solve number 21 and number 22 on page 9 by yourself. Once you're done, go ahead and hit play. If your answer for number 21 on page 9 was 1, you are correct. If your answer for number 22 is 1 over 19 to the 4th power, you're right. All we're changing is the reciprocal here, and we know that anything to the 0 power is 1. Let's go ahead and move on to our practice, okay? Let's do this part together on page 23. First, we're going to rewrite our problem. 3 to the 2nd power times 4 to the 2nd power equals, or times 5 to the 5th, or sorry, times all together to the 5th power. The next thing we do is we're going to separate our operations so we know what to do first in our PEMDAS. So what I did here was I simplified everything. I took the 2nd power out because I knew that the 2nd power was going to be multiplied by both 3 and 4. So my 2 goes out here in the outside parentheses, and then I start my operations with my innermost parentheses first. Okay, so now I have 3 times 4 equals 12. I have that 2nd power, and I bring down my 5 now. All I have is 1 parenthesis left, so I'm still going to do what's in my parentheses first. So I'm going to multiply 12 times 12. However, since I want to keep this as simplified as possible, I want to multiply my 2 times my 5, which equals 10. So my answer is 12 to the 10th power. So my solution is 12 to the 10th power. Let's try number 24 and number 25. What did you get for your solution? First, in number 24, I'm going to rewrite my problem. Then I'm going to simplify it so that I make my terms the same. I'm going to make it 9 to the negative 8th power times 9 to the negative 3rd power, because that's the easiest way to solve. The next thing I'm going to do is combine my like terms. So here I have 8 to the negative, or sorry, 9 to the 8 to the negative 8 minus 3. Okay, I'm just putting together this negative 8 and this negative 3. I'm putting it together up here. Then I'm going to combine negative 8 minus 3 on my number line is 11, negative 11. Okay, so now I have 9 to the negative 11th power. I'm going to make that a positive number, so it's going to be 1 to the 9/11th power. That is my solution. And number 25, the correct answer is 1 over 45 to the 6th power. And Isaac got this answer wrong because he divided the exponents instead of subtracting them. 45 to the negative 3rd power would be 1 over 45 to the 3rd power. And if you added the 3 and the 3 together, you would have 45 to the 6th power. So it's 1 to the 45 over 6. Your next task is to complete the independent practice pages 12 and 13